Hi, today's topic is firmware engineering. The chapter we are going to discuss is hardware architecture and design. Let's let's ask me a question. How a microcontroller and embedded system are structured? What kind of hardware component are typically in microcontroller system? So hardware in microcontroller structure are a microcontroller usually include memory, RAM and flash, an ALU, arithmetical logic unit, I/O buses, and maybe even timers or ADC, analog to digital converters. How does the hardware design ho- affect how firmware is written? Would you write a code same way for a computer with 2 GB RAM and one with 2 KB RAM? Embedded systems have limited resources and uh, must be efficient. Why do you think like C and assembly are preferred over high level language like Python and for embedded system? Think about think about how much control and efficiency each language gives you and what you just said about resources constraint. So uh, firmware has a limited resources. That's why instead of using Python, they use assembly level language, and or C type language, C language, C language and assembly language. C language is a high level language, but closer to the hardware than many others. Assembly is a low-level language, very close to the machine code. In embedded system, we often need to tie control over memory, timing, and hardware. Mhm. Would a language like Python, which is easy to write but use more memory, hides hardware details, be a good fit for something like a small sensor with 2 KB RAM? Why not Python but C assembly? Python uses more memory and runs slower because it needs an i- interpreter and doesn't give you direct control over the hardware. C gives a good balance, easier to write than assembly, but still efficient and close to hardware. Assembly gives the most control, but it is harder to write and understand. Why might a firmware engineer still choose to use assembly code even if most of the project written in C? Firmware engineer might use assembly for precise timing, direct hardware access, speed op- speed optimization, and tiny memory footprint. Even though most of the code might be in C for readability and fast development. A small part in assembly can help vary where every cycle and byte are counts. What is an embedded system? A computer system designed to perform specific tasks within the larger system. A combination of hardware and software specifically tailored for particular particular application. Applications of embedded system common in cell phone, automobile, industrial control system, consumer applications. Real-time processing. The ability to respond to external event on time. Critical for application like aviation, military, industrial control. Even a small delay can have serious consequences. Resources constraints. Embedded systems often have limited memory processing or supply. The design must be maximize efficiency within these constraints. Program langu- Programming language for embedded systems. C and C++ are widely used high-level language embedded development. Assembly low-level language for direct hardware control. Systems often require both high-level logic and low-level hardware interaction. Low-level hardware interaction. Key challenge work Key challenge is working closely with hardware. Require knowledge of microprocessor, memory system, peripheral components. Code must be efficient and optimized for specific hardware. Handling real-time constraints. Programs must respond quickly to external input, handle interrupt and event-driven scenarios. Timely is execution is essential for sy- system stability and safety. Skills required for embedded programming. Combination of hardware knowledge, software development skills, understanding of real-time systems, ability to write efficient, optimized and hardware software code. What is RTOS? They are designed for real-time application required timely requiring timely and res- pre- predictable response. Use systems like avionics, industrial process control, robotics, automation. Key feature of RTOS is primitive multitasking, real-time scheduling, fast interrupt handling, small memory footprint, optimized for speed and efficiency, stable for resource constrained embedded system, bare metal system, run without an operating system, and hardware single program manages hardware access, logic, control logic, interrupt handling, no OS abstraction, or systems services. Advantage and challenges for RTOS: easier to develop and manage the complex applications, built-in task scheduling and inter-task communication, more versatile and maintainable, require more resources, may introduce slight overhead. Advantage and challenges for bare metal system: highly efficient and fast, no OS overhead, precise control over system behavior, more complex to develop. Developer must handle all low-level functionality manually. Choosing between RTOS and bare metal. Use RTOS when application need multitasking, easier scalability, and real-time scheduling. Resources are sufficient to support a lightweight OS. Use a metal system when performance is critical, system is simple, or highly resource constrained. You need full control but are prepared for higher development effort. Conclusion: bare metal system, there is no operating system. On real-time operating system, RTOS are lightweight OS that can handle tasks with strict timing. In bare metal system, who is responsible for deciding which code is run when? In bare metal system, since there is no OS, actual the controls the flow of program like function runs first when the check sensor when to check sensor or when blink on LED. Is is it a system decide or you decide, a programmer decide? In bare metal system, programmer controls everything. When code runs, how tasks are scheduled, usually in a loop or with interrupt. How timely handled. If managing everything manually can get messy, especially with many time sensitive tasks. What might be the benefit benefit of using RTOS instead? Now, RTOS helps system to react more predi- predictably and efficiently, scheduling tasks based on priority and timing, handling multitasking. Make sure the make sure critical tasks run on time. In what kind of situation might an RTOS be more helpful than bare metals programming? One, avionics must be respond to sensor input and control system with precise timing. Industrial control runs many tasks at once, like reading sensor, updating display, controlling motor, all strict timing rules. Robotics and automation needs to make fast decisions based on sensor data and move accordingly. In those cases, RTOS helps keep everything organized, predictable, and on schedule. Sometimes something very hard to do with just bare metal code. Next, what is an interrupt? Interrupt is a mechanism for software or hardware to request immediate attention of the processor. Interrupt pause the current task to handle a high priority, allows the efficient response to asynchronous event. How interrupt works? When interrupts occur, the processor saves the current state, execute the interrupt service routine (ISR), perform the required action, and return to the previous task once ISR completes. Type of interrupt. Hardware interrupts. General generated by external device like keyboard, sensors, network card. Sent via dedicated hardware lines. Software interrupt. Generated by software instructions. Typically used for system call system calls or executions. Why are interrupts important? The interrupts enables the processor to react quickly to important events. For example, user inputs and ti- timer expiry. Avoid polling, which waste the processing power. Improve improve the efficiency and responsiveness. Interrupt priorities. Interrupt can be assigned priorities. High priority interrupt preempt lower ones. Preempt lower ones. Ensure the critical events are handled first. Interrupt embedded in the embedded system. Used to handle used to handle sensor input, per- peripheral communications, timer and control signals. Critical for real-time performance and system reliability. Interrupt in RTOS versus bare metal system. RTOS provides predirect- predictable and structural interrupt handling. Uses interrupt to trigger tasks and manage system timely. Easier to manage with building scheduling. Bare metal developer must manually manage the interrupt. Greater control but higher complexity and risk. Timing and priority must be implemented by the programmer. Conclusion. Interrupts are fundamental concept in embedded system programming, essential for performance, responsiveness, and reliability. Proper interrupt handling improves system behavior, especially in real-time applications. Thank you.